Great. What we have accomplished this Sunday. So we're looking on balls of fluid where we have particles sitting inside a box. The volume of the box is V. All the different particles are not interacting. They have only kinetic energy. And they are bosons. Okay. Now, we managed, by using the grand canonical ensemble, we managed to calculate the grand canonical potential, which is minus G0 divided by beta, integral from 0 to infinity, log of 1 over 1 minus e to the power minus beta, epsilon minus mu, d epsilon, d epsilon. Then we had a very lengthy integration procedure where we used Feynman principles 2. We expanded the 1 over fugacity in terms of Gaussian integrals, etc., etc., etc. But eventually we use this deep side to d mu equals to minus n, and we obtain a wonderful result for n. N was G0 d lambda t to the third power, polylogarithmic function f3 over 2 of the fugacity, where fugacity is e to the power beta mu, lambda t, the thermal wavelength, is, what is this thermal wavelength? It is square root of 2 pi h bar squared divided by mk boson t, and the polylogarithmic function f alpha of x is a sum. I goes from 1 to infinity, x to the power I multiplied by 1 over I to the power alpha. Okay, now the problem occurs when we look on this expression over here, and specifically the properties of this polylogarithmic function when fugacity goes toward 1, which means that mu, so the mu goes to 0, where 0 is the lowest energetic state, or ground energy, which is not exactly 0. Okay, but we'll see it in a second. We know that the fugacity goes to 1. Okay. And we know that f3 halves of fugacity goes to 2.61. Now, why it's a problem? Problem is that it limits the maximum value that the average number of particles, or the number of particles that we can have inside the system. So, if you look on this, f3 halves as a function of the fugacity goes like this. So the slope is diverging, this limit of 1. The function itself, it is limited. Now, of course, when you look on this definition, when x is larger than 1, okay, basically we have something to the power I, and this something is larger than 1, so the function will diverge, but exactly at 1, it converges to a constant value, which is smaller than infinity and has this number of 2.61. Okay. Now, this means that f3 halves of fugacity, or basically if we can write it down as n multiplied by lambda t to the 3rd power divided by g0v, which is f3 halves of the fugacity, is smaller than 2.61, or lambda t to the 3rd power n g0v is smaller than 2.61. But we can make v small and we can make n large, and definitely it's a funny law of nature that somehow it limits the number of particles that we can put inside the box. Right? So something went extremely wrong over here, and think about it. If we have n which is on the order of 10 to the 23, something is erroneous about this relation. This means that we messed something somehow during the process. Okay? So now we want to try and explain why this relation is wrong, basically, and where we took the erroneous turn. So there can be several potential problems. One, of course, is that somehow we calculated erroneously the grand canonical potential. But you can look it over and it seems fine. Maybe we haven't did the derivative. Basically, well, it also should be fine. So everything that we look upon, everything looks okay. But there was several assumptions that we made. And those assumptions were, well, actually, we don't have a continuum spectrum, right? Because the energies are p squared divided by 2m, which is h bar squared k squared divided by 2m. Okay. And this means that this is a discrete spectrum, right? How so? Because this is h bar divided by 2m, and we have 1 over lambda x squared plus 1 over lambda y squared plus 1 over lambda z squared. Where are the lambdas? Lambda x and lambda y and lambda z are the wavelength of the particle. Okay. So this is described in the following sense, since we know that n lambda nx lambda x divided by 2 equals to L, and we know that ny lambda y divided by 2 equals to L, and we also know that nz lambda z divided by 2 equals to L. So those wavelengths are the wavelengths of a sinus of cosines based on the fact that the wave function of each of the particles zeroes out at the boundary of the box. Yes?
You have the 2 pi factor because k is 2 pi over lambda.
So it's not h bar, it's going to be h, right? Okay.
No,
It's not h.
It is h bar.
Sorry? No, it's
h bar carrying became h. H was 1 over.
The first one is h bar and the second is h.
okay, this.
This is okay. This is h.
This is h.
The other one is
And this is h bar. Yes. Okay.
But shouldn't we have the same problem with the fermions, and we didn't have that problem?
So we can look on the fermions, but there was a 2 pi over there. There was a factor of 2 pi over there. Okay.
I mean the discretization.
Oh, so first of all, I will explain it. Yeah, I thought you're referring to the 2 pi over there. I will explain what's the problem and where it's coming from. In a second. Okay, so when we plug inside all of those things, what we have is we have h bar, no, it's simply h squared 2m, and what we have inside, so instead of lambda x, I write down nx L nx divided by L divided by 2, squared plus ny divided by 2l squared plus nz divided by 2l squared. Okay, so this is the energy. And since we are using that L, it is V to the 1/3, we are going to have H to the 2, 8, V to the 2/3, and here we have nx squared plus ny squared plus nz squared. Okay. So this is the discretization. Okay. This is the all the different nx and ny and z can have numbers 1, 2, 3, 4. And the ground state is when one of those is exactly 1. So we, instead of saying that we have a continuous epsilon, the epsilon, our energy, it depends on the three quantum numbers, and x, and then y, and then z. Okay. And this means that the spectrum, as we knew from the start, is not really continuous, right? It's discrete. So if I'm looking on my epsilon, I try to convince you that everything here, and I already did it for fermions, everything here is very continuous. But actually, when you look on this, well, it's not exactly continuous. We have states, right? And the only question is, are those states are densely packed together, or the fact that they are not exactly, the distance between two states is not exactly 0, but it's something, okay, affects our calculation. So the first thing to check is, okay, so what is the difference? What is this minimal? If I'm looking on this, I'm zooming in, and I have different states, and I'm asking, what is this delta epsilon? If this delta epsilon is large, so yeah, of course, the transition from summation to integration is a bad thing to do. But if this delta epsilon is good, or I'm sorry, good, it's small, well, then the transition should be okay. And your claim regarding, well, we did it already for the fermions and it worked okay there, it's a supportive claim. So it worked for the fermions, why shouldn't it work also for bosons? And so one can guess that the discretization is not a big issue, but let's look on it. So what is, if we take the lowest state, epsilon 1 and 1 and 1, this is the ground state of the particle, and we look on the first excited state. And we subtract between those two. So this is the delta epsilon. Okay? The delta epsilon that we have down here near the ground state. So according to this formula, what we have is the following. So it's h squared divided by 8 volume 2/3. And here we have 4 plus 1 minus h squared divided by 8 volume to the 2/3. 1 plus 1 plus 1. Okay, so here we have 6 h bar divided by 8 v to the 2/3 minus 3 h bar squared divided by 8 volume to the 2/3.
You need to divide by m.
I needed to divide by m. Oh, okay, so 2m, 2m, 2m. So m over here. Yes, thank you. It's crucial. We have m, we have m, we have m, and we have m. Thanks. So in total we have 3h squared divided by 8mv to the 3rd. Now let's take and compute this for helium-4. we're looking on helium-4, and the mass is approximately 6.6 to 10 to the minus 7 kilograms. And we're looking on a liter volume, which is 10 to the minus 3 cubic meter. The third. An engineer. I'm sorry, I'm joking. Okay, so we plug these numbers inside, and what we get, that epsilon 2, 1, 1 minus epsilon 1, 1 is on the order of 2.5 multiplied by 10 to the minus 37 joule. Or if you want to use this on the order of temperature, because it's more intuitive what is the temperature, so E211 minus E11 divided by K Boltzmann, it's approximately 10 multiplied by 10 to the minus 14 Kelvin. What it means is that even for extremely low temperatures, okay, very close to zero, those differences are negligible. Okay, so in order to feel, for the particles to feel those energies, this discretization of energies, we need to go to temperatures as low as 10 to the minus 14 Kelvin. So basically what it says that we don't care about this discretization whatsoever. Okay? So the transition from a discrete spectrum to a continuous spectrum, perfectly fine, because those differences here are extremely small. Okay. So what's then the problem? Okay. So the discretization was fine, but maybe we omitted a very crucial point, because what do we know? Let's look on the N0, which is average number of particles at ground state. What is this average ground number of particles of ground state? So we know how to calculate it. We don't need anything about the continuous spectrum, discrete spectrum. We don't need the ground canonical potential. We know how to calculate this from scratch, right? Using the partition function, and we already done it. And it is 1 over e to the power beta epsilon minus mu minus 1. Now this epsilon is 1, 1, and 1. This is the ground state. Now, we know that something funky is going on when we lower the temperature. Okay? When we lower the temperature, we know that when T goes to 0, mu goes towards 0. Okay? And at least at this lower temperature regime, okay, we can say the following thing. So N0 is going to be very much larger than 1. How do I know this? Well, because I can expand this, I can say that e to the power beta epsilon 1, 1 minus mu minus 1, it is approximately, and I'm using the Taylor expansion of the exponent.
But beta is large.
Sorry?
But beta is large.
Okay, so I assume that this guy is small. Okay? Plus beta epsilon 1, 1, 1 minus mu minus 1. Okay. So what I'm saying is that N0, it is beta, or K Boltzmann T, divided by epsilon 1, 1 minus mu. Now, your question is your point is very crucial, because you're saying, well, who goes to 0 faster? The T to the 0 or mu to epsilon 1, 1, 1. Now, let's assume that I can have indeed a large number of particles at the lowest level. The moment that I have the large number of particles, I'm saying that the denominator it's much, 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 much smaller than k Boltzmann T. Okay? So I do assume that there is a situation where my chemical potential is basically going towards epsilon 111. But and this is the limit that I'm exploring. Remember, all of this, all the problems started from what? They started from that the fugacity is going towards 1. The fugacity is going towards 1, mu going to 0. Okay? I'm assuming that it happens at low enough temperatures. Why it's happening for low enough temperatures? Because I know that mu is a growing function of T. Sorry?
What do you mean if it's growing when T getting smaller? So it's decreasing.
It's increasing. Right? Mu is increasing as the temperature is lowered. Okay? So for fermions, as the temperature is getting lowered, mu is getting smaller, and it's the other way around for the bosons.
Function increases when the parameter decreases, so it's decreasing.
Mu is negative, remember, and T is decreasing, and mu is increasing. Okay? Remember, mu have to be negative. It's going towards 0 as we decrease T. And as we increase T, it's going to be more and more negative.
So mu as a function of T is decreasing.
Mu as a function of T is a decreasing function. Yes, but it's negative. It's getting away from 0. Okay, so let's look on this guy now and try to approximate this in the following sense. So we know that something bad happens in this limit when mu goes to 0. We look on this number and we say this is the occupation fraction, okay, of the particles that are sitting at the ground level. Now, we know that, well, the continuum spectrum and discrete spectrum are basically exactly the same. So the other guess where the problem have risen from is that maybe the function, okay, so the spectrum is continuous. This is fine. But maybe, just maybe, the function that we integrated over, and we integrated over what? We said that n is a sum over all the different epsilons and epsilon. Okay? So the average number of particles is a sum of all the different numbers, occupation numbers of particles of different levels epsilon. Now, the next step was to basically make this summation an integral. And we checked this portion when we said, well, the discretization and the continuum spectrum are exactly the same. But we haven't checked how this function itself is behaving. Right? So we know that the transition from summation to integration is just fine. But when you have to check this transition, there's two things to check. One, are the energetic levels indeed closely packed together? And this we checked. And the other thing to check is, well, maybe this function behaves not nicely. Okay? We know that it's not continuum because it's jumping from one state to another. But when those jumps are too large, you cannot make this transition from summation to integration. Basically what I'm trying to say, if this function have divergences or it's represented by delta functions, you cannot simply make this transition from summation to integration. Okay? And what we see is that when mu goes towards the ground state level, n0 becoming very, very large. Okay? So if you look on as a function of epsilon, and we look on an epsilon, And we know that, well, the epsilon spectrum is discrete. So in reality, we have discrete sets of an epsilon. Right? And if we just have some numbers over here, okay, what we have done is that instead of summing up, we said the sum over all the different n epsilon is simply the integral below this line. And this transition is always a good transition as long as these delta epsilon are small, and there is another condition. And as long as nothing funky behaves with the different values of an epsilon. Now what we have, so this is what I had, and probably maybe you had in your mind when I made this transition from a summation to integration. I have discrete spectrum of the energies. I have discrete values of number of particles at each state, and I, instead of summing up, I perform an integration. Great, nice. Okay, but if we have the following thing, what if we have a very large value at 0, right? Some are sitting over here, and all the other different values are small. Okay. So what I tried to perform by making a transition from a summation to integration, I said, let's compute the value or the integral of a function. You see, the thing is, the contribution of one single point is not marginal. Okay? It's basically dictates the behavior of the whole integral. And when you perform this transition and you forget to treat properly this specific function, you can say, well, maybe it's like a delta function over here. Okay? And if you're not doing this, there are going to be discrepancies and there are going to be problems in your transition from summation to integration. So what I'm trying to check is, let's see, and maybe this is the case at our hands. Right? Maybe the behavior of the function, the behavior of the number of particles at the lowest level, it's extremely big, it's extremely large compared to what? Compared to the occupation of the next levels. Okay? And if this is indeed the case, then the transition from summation to integration is not going to be correct. Basically what I'm trying to say, maybe we have to treat specifically the lowest level and make its contribution to the whole integral special. Okay? Not just say, well, it's, you know, it doesn't matter. Because if you think about it, as long, you know, I try to remind you whatever you learned in your undergrad studies at the first year course infig class. So when those differences are small, you don't really care if I take a single point and I kick it out of the sum, okay, or of the integration, because the contribution of a single point is always negligible. Okay? This is the transition due to Riemann sums and etc. etc. But here, and this is right, unless the value of the function at this specific point actually diverges, you cannot neglect this point. Right? And what we have done so far, we completely neglected or tried to neglect whatever happens at the ground state. And what I'm trying to say, so maybe when we see that this n0 can be very large when the fugacity goes to 1, maybe this is the discrepancy.
And we should expect this because since we are dealing with bosons and they don't fulfill the Pauli exclusion principle,
yes,
and we are thinking that the principle of minimum energy, we can assume that particles will like to sit in the minimum energy, right?
Exactly. Now, you ask also the question, why this work for fermions? For fermions, the occupation numbers 0, 1, nothing can diverge over there. Here, there is a specific point that can actually be extremely big because we expect the particles to sit at the lowest level. Okay? All right, so what actually happens here? Let's try and see this. I want to so I know that this n0, okay, this n0, which is, we know it's over k Boltzmann t divided by epsilon 1 1 minus mu. Okay, and when mu is small, okay, let's assume that mu goes towards 0. Okay, and we plug this value of epsilon 1 1 when we already have. So this is for t equals, let's assume 10 Kelvin. Okay. What we are going to obtain is that this number is on the order of 10 to the 22. Okay. So I'm using that the mu goes almost 0. I'm using epsilon 1 1 as the value that we had before. I'm submitting here t as 10 Kelvin, and this is what I obtain. Now, I want to compute this is n11. I want to compute the ratio between n211 divided by n111. Okay? And if this ratio is not big, it's approximately 1, 2, or 3, then whatever I have done so far is fine. But if this ratio is extremely large or extremely small, then the function is not nearly continuous. Okay, you had a question?
How do you know what's mu in
I submit that this is almost 0. I basically submit this as the value that I have, okay, and this I set mu goes to 0.
But when you really calculate, when you insert a value, so how do you, because if mu is equal to 0, then the ratio is just the ratio between epsilon 111 and epsilon 211, which is like.
You'll see. Yeah, but okay. Let's see in a second how I do it. Okay, this specific ratio. Okay, so where's my page? I do the following thing. So first of all, what is n211? It is 1 over e to the power beta epsilon 211 minus mu minus 1. Now, everything here is small. So mu is almost 0. Epsilon 211 is also small. All right. So I can say that this is just simply as k Boltzmann t divided by epsilon, or let's write it down, 1 over 1 plus beta epsilon 211 minus mu minus 1. Okay, I'm again using the Taylor expansion of the exponent for a small value of beta epsilon 211 minus mu. This is approximately, so this is a k Boltzmann t divided by beta epsilon 211 minus mu.
Without the beta.
Without the beta, thank you. Right. And now I'm saying the following thing. This is t. So this is t, and here I have epsilon 211 minus epsilon 11 plus epsilon 11 minus mu, and this divided by k Boltzmann, and this divided by k Boltzmann. So the next step, I want to compute n2 by n1. So n211 divided by n11. It is t divided by epsilon 211 minus epsilon 11 plus epsilon 1, 1, 1 minus mu divided by k Boltzmann divided by k Boltzmann. All of this multiplied by 1 over, and what is n11 was? It is t divided by epsilon 1, 1 minus mu divided by k Boltzmann. Great. We don't care about t over here. And we have 1 over epsilon 2, 1, 1 minus epsilon 1, 1 divided by epsilon 1, 1, 1 minus mu. Okay? Plus 1. Okay? So the next thing is to compute what is epsilon 1, 1, 1 minus mu divided by k Boltzmann. So this I already told you. This is 10 to the minus 21 Kelvin. And epsilon 211 minus epsilon 111 divided by k Boltzmann. I don't care about the mu over here when I'm looking on this term. And this is 10 to the minus 14 Kelvin. Yes?
Epsilon 211 minus epsilon 111 is the same as epsilon 111 because
10 to the minus 14. This is what we got before.
but but you said mu is equal to 0.
Almost 0.
How close?
Okay, how close? Where I choose this number? The total number of particles in the liter. What it is?
10 to the 23.
2023. Okay, so this guy is basically 1 over. So it is like I took a specific portion of the particles that are sitting at the lowest level.
But you assume that most of the particles are in the states, in the שלב המדרגה היסודית.
I assume something the following. What happens if I push? So this is a physical assumption. What happens if most of the particles trying to penetrate the first or the ground level? Okay. I know that very large portion of them is going to sit over there. Okay. Now, what happens at the next excited level? Okay. So this is the question. The question is, I know from physics that most of the particles. Let's assume what happens at the 0 temperature. Everybody have to sit at the possible lowest level, and this is the ground state. Okay. Now I excite my temperature a little bit higher. When I excite my temperature a little bit higher, I am going to have a spillage of particles from the ground state to the next levels. Okay. The question is the spillage going to be continued? Or is the spillage is going to be, well, I have a delta function over here and something really small that occurs in all the other states. So you're right, I don't know what exactly mu, but I know that the number of particles at the lowest level is of the order of 10 to the minus 21. Okay. So when I plug all these numbers, I get that n211 divided by n11 is 10 to the minus 7. Now I use this, well, specifically this approximation at temperature which is 510 kelvins, right? And we got that, well, there is a number which can be very large at the lowest level, and I assume that nearest neighbors or nearest states are also going to have a big number of particles. Okay, maybe not as big, but big enough. Now, but what we got is that, well, there is a bunch of particles at the lowest level for low temperatures. And when I consider the next level, the next energetic level, which is separated from this ground state by only 10 to the minus 14 Kelvin, I obtain a huge drop-off in the number of particles. Okay? And this is crucial. It's basically saying that I cannot properly integrate this function from 0 to infinity. Okay? I need to take this single level into account. not just throwing it away, not assuming that the function is continuous. The function is not continuum and not nearly continuum. There is a huge drop-off. So we have to treat the lowest, the ground state, separately, and then combine the contribution of everybody else. Now, where exactly it's going to happen? So we have something bad happens as f of 3/2 of this fugacity goes toward 2.61. We basically found that there is a problem with our calculation when this polylogarithmic function getting closer and closer to this number. Okay. So we basically can say, well, let's try and see for which temperatures this start to occur. Right? Which temperature this occurs. So what we have is that we have G0, V, NE, lambda T to the third power is approximately 2.61. Now, we substitute here the value of lambda T, which is, if you remember properly, lambda T was, I never remember this thermal wavelength.
What's in the denominator?
Just a second. So what we have is the following. We know that N is G0V divided by lambda T to the third power F 3/2 of the fugacity. We know that this function is limited by the value of the fugacity when fugacity goes to 1, so all of this is smaller than 2.61. Okay. And lambda T, 1 over lambda T, is a square root of mk Boltzmann T divided by 2 pi h bar squared. Okay. So let's put back everything and assume that this 2.61, okay, that this guy is exactly 2.61, and let's find the temperature for which this funky behavior occurs. So basically what I'm saying is that this N equals to G0V, 1 over LT is M K Boltzmann T divided by 2 pi H bar to the power of 3/2, and here I put 2.61. So I'm going to have a temperature, I'm calling it critical temperature. Why critical temperature? Because for this specific temperature, something is fishy, because N cannot be larger. So for this TC, which equals to N divided by 261, G0V to the power of 2/3 multiplied by 2 pi H bar divided by M K Boltzmann. And if we substitute for helium-3, we obtain that Tc equals to approximately 3 Kelvin. So if we take Avogadro number of particles and we take a volume which is 1 liter, so it's T⁻³ cubic meters. We substitute the mass of the atom and we substitute all the different other constants. We obtain that when we get towards this critical temperature, okay, something going on. So what is this something? So we already know that there is accumulation of particles at the ground state, and it's much larger than the accumulation of particles on the next state. Okay. Now, when this number is actually checked in for in experiment for helium-4, Tc, so this is experimental value, is approximately 2.2 Kelvin. So helium-4 at approximately the same temperature, so this means that the theory is pretty much correct. The helium also starts to behave in a fishy fashion. So what happens to helium? There is a transition that's called superfluidity. This helium-4, it's basically flows from one place to another without any friction. Now, I cannot explain why exactly it happens. It's due to some quantum mechanical procedure and coherence. Okay? But helium crosses to a different state of matter exactly at this temperature, or very close to the temperature that we calculated. So something going on at this critical temperature, and we know that this is associated with this huge drop-off of the number of particles that are sitting at the lowest state. Okay. I'm almost done, but I have left 10 minutes. So tomorrow I will spend another 15 minutes in properly explaining the phenomena. Because what is happening actually, this is called a Bose-Einstein condensation. And we see that the number of particles that are sitting at the lowest level is huge and disproportional to the number of particles that are sitting in the next level and the next level, and etc., etc. So what happens is that a large portion of total number of particles is accumulated at the ground state, and they behave differently. So if you want to remember the difference between the fermions and bosons, it can be summarized in a very simple picture. So for fermions, due to Pauli exclusion principle, this is epsilon, they sit one on top of each other. Okay. For bosons, this is epsilon, they sit, all of them start to sit at the possible lowest level. We can say Stas is it's clear because when the temperature is 0, this is what we expect for fermions. They fill up all the different levels because of the Pauli exclusion principle, which is great. And for bosons, well, the system always, you have told us, and Bina have told us, that the system or any particle wants to stick to its lowest possible energy. The ground state is the possible, lowest possible energy. So everybody are going to sit over here, okay, at a temperature equals 0. So this picture is not new and not, what you were trying to say. The nice thing about bosons is that this occurs at the critical temperature of 3 Kelvin or 2.2 Kelvin. So you actually start to observe this behavior not at T equals 0, but at finite temperature. So we have a transition to something that we expect to appear only at temperature equals 0, but we cannot reach temperature equals 0, never. But this expected behavior at T equals 0 actually appears at finite temperature. Okay? This is called condensation. And the big surprise about bosons is that condensation transition occurs at Tc, which is greater than 0. Now, I explain exactly what is the number of particles, how we calculate it, how we take into account this lowest energetic level tomorrow. Thank you.
Thank you.